In one of our lab assignments, I asked you to evaluate the factors of safety fatigue lifetimes for the head bolts on a Ford 6-liter diesel engine. This is an example of the block, including the pistons, and you will recall that in this particular engine, there were 10 total head bolts on each side of the V8 diesel engine. This is a 6-liter diesel engine with a 95 millimeter cylinder bore, 105 millimeter stroke, and there are 4 valves per cylinder. It generates 325 horsepower at 3,300 RPM. If you look at the engine, you will see that there is the cast iron block, which is capped by a 95 millimeter thick cast iron head, which then carries a 51 millimeter thick aluminum rocker carrier, and the head bolts that are used to hold these components together pass through the rocker carrier, through the head, and down into the block, and the block is threaded. So we have these large bolted fasteners that have to hold the head onto the block and sustain the pressure that is generated by combustion of the diesel fuel. The fasteners are metric 14 by 2 and are 238 millimeters long. The threaded length is 133 millimeters, leaving the unthreaded length at 105. Bolts are ISO grade 10.9 M14 by 2, so the diameter is 14 millimeters and the pitch is 2 millimeters. These are designed to be torque to yield bolts, and they are grade 10.9, and that means they have a yield strength of 940 MPa. We are to torque the bolts to yield. And so we can multiply the yield strength by the threaded cross-sectional area of the bolt, which is 115 square millimeters, and we can find that the overall, in the manufacture of the 6-liter diesel engine, the head bolts are designed as torque to yield bolts. That means we are going to tighten them enough that they yield. The preload on each bolt at manufacture is given by the yield strength times the threaded cross-sectional area of the M14 bolt. You do this calculation, you find that the initial load per bolt is 108,100 newtons. During operation of the engine, the total bolt load is going to be equal to that initial load plus a joint stiffness times any additional load that is thrown onto the bolt by the combustion pressure. Internal combustion engines use gaskets between the block and the head to retain the internal pressure of combustion. Now, I want to take a look at some of the generations of the Ford diesel engines. The 7.3 liter Powerstroke was built from 1994 to 2003, and this is an example of a gasket set for the 7.3 Powerstroke. And you will notice something, that these gaskets surround the pistons. You will notice holes for the head bolts as well that hold the head onto the block. And in the 7.3 liter Powerstroke, you will see that there are 1, 2, 3, 4, 5, 6 bolts per cylinder. In 2003, Ford introduced the 6-liter Powerstroke to replace the 7.3. The 7.3 was known as an incredibly long-lived engine that was very reliable. When they moved to the 6.0 liter, it had a higher specific horsepower, it was quieter, it got better economy, and it was in many ways, as manufactured, a better engine. Unfortunately, they had a huge problem with head gasket failure in those engines. And here's an example of a head gasket for the 6-liter Ford diesel engine. And there are 1, 2, 3, 4 bolts per cylinder holding the block and the head together and compressing this gasket. This gasket has to make sure that there is no leakage during the combustion process, and you absolutely want to make sure that there's no leakage of coolant fluid, which passes through vias around the block to keep the engine from overheating. If that fluid interacts with the combustion chamber, all bets are off, and so the engine fails. They had a huge number of failures with the 6-liter Powerstroke diesel. They went from 6 bolts per piston to 4 bolts per piston. Well, they didn't have a lot of luck with this engine. They had a lot of warranty claims and a lot of early failures. So they moved to a 6.4 liter Powerstroke, which retained the 4 bolt per cylinder pattern, but they moved to larger diameter head bolts. So Ford gave up letting somebody else build their diesel engines, and they took the construction in-house and designed the 6.7 liter Powerstroke. You'll see they returned to the 1, 2, 3, 4, 5, 6 bolts per cylinder. We're now ready to go back to the 6 liter diesel engine, where we have 4 bolts per cylinder. We've already worked out that if we torque these bolts to yield, then the preload in each bolt is 108,100 newtons. The internal pressure in the cylinder during ignition of the diesel fuel is roughly 18.6 megapascals. The upward directed force pushing the head off of the block is going to be the projected cross-sectional area times the internal pressure. Well, that cross-sectional area, the bore, remember, the diameter is 95 millimeters. So we take pi times 95 squared divided by 4, multiply that by the internal pressure, and we get 131,841 newtons total upward force acting on the head. There are 4 bolts, and so the load per bolt is 32,960 newtons. We are now ready to use our spreadsheet to determine the bolt and member stiffnesses. It asks us if we are bolting into a threaded plate. We say yes. Our bolt diameter is 14 millimeters. It's a coarse thread, 238 millimeter long bolt with 133 millimeter threaded length. Its cross-sectional area is 115 square millimeters. Model the top plate as aluminum, 51 millimeters. Remember, the second plate, the head, is 95 millimeters thick, but there's this 10 millimeter bore hole in the block before the threads start in the block. So I just added 10 millimeters to the top head thickness and made it 105. And then I made the bottom plate just a little bit more than the stroke. And so I have 2 cast iron. The block is cast iron. The head is cast iron. The rocker carrier is aluminum. From that, I find that my bolt stiffness is 174.5 meganewtons per meter, and my member is 782.6 meganewtons per meter. We're now ready to move into the bolt fatigue section of our spreadsheet. In order to do that, we need to know the ultimate strength of the bolt. Well, we go to tables of material properties, and for the M14-2 grade 10.9, the ultimate strength is 1040 MPa. The proof strength is 830. The endurance strength is 190 MPa. The bolt preload, we've already said, is 108,100 newtons. Our member stiffness, 782.6. The bolt, 174.5. Our threaded area, and now our maximum load applied to any given bolt in the 4-bolt connection is 32,960 newtons. Our minimum is 0. From that, we calculate our load amplitude, our mean. We have our joint compliance, our stress amplitude, our mean stress, our initial stress, which was 940 MPa. That's the yield strength for a grade 10.9. Our opening factor of safety is good, it's 4. Our proof strength, of course, we're loading to the yield, so our proof strength factor of safety is less than 1. But the troubling thing here is our Goodman factor of safety is 0.59. It seems that, given the loading conditions, this was an ill-conceived design from the start. Given all the problems with the 6-liter Powerstroke engine, Ford introduced a 6.4-liter Powerstroke engine, which changes things quite a bit. But one thing we can try out right away is, what if they increase the diameter of the head bolts from 14 to 16 millimeters? If I do that using my spreadsheet, what I find is that it changes the bolt and member stiffnesses. The bolt stiffness is now 230, the member 914 meganewtons per meter, and we change the threaded cross-sectional area from 115 to 157. But more importantly, if we preload to the same levels, we find that our Goodman factor of safety is now greater than 1. It's moved up to 2.57. So just choosing a larger bolt diameter would have saved them a world of grief. In the next video, I'll show you how to make a simple representation of the diesel engine and how to model it in Fusion 360 and run a finite element analysis. Use that to evaluate the gasket pressure between the head and the block.